Hi guys, welcome. We're day 19, so we're starting into a new unit. We're looking at lessons 61 and 62 today. So lesson 61, we're dealing with sequences. So this is similar to a function where we have a rule that we follow, but a lot of times we'll be given a pattern of numbers and we'll have to work backwards to try and find the sequence. So some new terms here. A sequence is an ordered list of numbers. We have a sequence right there, 3, 6, 9, 12. The terms that follow a certain pattern or rule. So this would be our first term, second, third, fourth, and continuing on. So these are the first four terms. So if we're only given one or two numbers, we may not be able to find the pattern. Like, well, from 2 to 4, well, that could have been adding 2, that could have been multiplying by 2, it could have been 2 squared is 4. So we would have to know, 2, 4, 6. Okay, we're adding 2, or it's multiples of 2 every time. In this case, we look at 3 times 1, 3 times 2, 3 times 3, 3 times 4. Okay, so we're adding 3 each time, so that's the pattern. So if we want to find the next however many terms, okay, we could just take it out. The sequence is an example of arithmetic sequence. An arithmetic sequence has a constant difference between terms. So plus 3, plus 3, plus 3, plus 3. Okay, so by subtracting consecutive terms, we find the constant. 21 minus 18 is 3. 18 minus 15, 3. 15 minus 12 is 3, and so on and so on. Okay, this one, well, 1 plus 2 is 3, but 3 plus 2 is not 9. Okay, so this one is not arithmetic. We have 1, 3, 9, 27. So if we look at that, each term is 3 times the preceding number. 1 times 3, 3 times 3, 9 times 3, and so on. So this one, it's going to get bigger at a faster rate because we're multiplying. So this is a geometric sequence. So arithmetic, we're just adding by a constant. This one is geometric, and we can find this by doing the division. So 243 divided by 81 is 3. 81 divided by 27 is 3. 27 divided by 9 is 3. 9 divided by 3 is 3. 3 divided by 1, okay. So the term of a numerical sequence has a position and a value. The position of the term, such as first, second, third, is often called the number of the term, and we'll use n. So when we're drawing out sequences, functions in the past, we've used f of x or y and x. For sequences, we're going to use n for the number of the term and then a for the value. So our first term was 3. Okay, so we don't have a 0th term. Our first term, our second term was, okay, this is looking at a different one. The value for this would be 6, 3 would be 9, 4 would be 12, 5. So this, for our arithmetic one that we were looking at, 1, 2, 3, 4, 3, 6, 9, 12. And so we could plot those. It's going to be linear because it's going up by 3 each time. This one is geometric. We're multiplying by 3. So our first term was 1. Our second term was 3. Or we could think about this, it's 3 to the power of 0, 3 to the power of 1, 3 to the power of 2, 3 to the power of 3, and continuing on. Since we're multiplying by 3, so it's going to go up, and it's going to have that J shape to it because it's going to accelerate and go up at an exponential rate. So they're going to have two different shapes to their graph. So if we have 3, 6, 9, 12, write a formula for the sequence. So we're given a set of numbers. We're going to have to work backwards to try and find our rule. Okay, so we're going to write our formula. So the number and the value. So we'll use a for value times the number in the sequence equals 3n. Okay, so this doesn't mean a times n. We would say a of n. So the n is the little n after the a is called the subscript. The expression a of n means the value of the nth term. So whatever we put in for, if we put a of 3 down there, that doesn't mean our value times 3. That means where n equals 3, what is our value? So, and then the rule is 3n. 3 times 1 is 3. 3 times 2 is 6. 3 times 3 is 9. So once we have the rule, it's really nice because then we can say, well, if a of n equals 3n, what's a of 20? We could sit there and go 3, 6, 9, 12, 20 times, but it's going to be a lot easier if we know, oh, this is saying a of 20. Well, where n equals 20, we put in 20 for n. So a of 20 equals 60. So we could calculate out by going by hand, but if we're trying to find the 20th or the 50th or the 100th term, it's going to be pretty time consuming to do that out by hand. Whereas if we have the rule, we just plug in the number, just like when we have an input and an output, we put in our input, we get our output. Our input was 20, our output was 60, so we're done. One, 3, 9, 27. As we said, the a of n equals 3n. Well, 3 to the power of 1 is not 1, it's 3. So for this one, it's 3 to the power of 0, 3 to the power of 1, 3 to the power of 2, 3 to the power of 3. So what we do is a of n equals 3 to the power of n minus 1. So whatever that number is, the number, that term, minus 1, and then 3 to that power gives us our value, a. So our first term, n is 1. 1 minus 1 is 0. 3 to the power of 0 is 1. Any number to the power of 0 is 1. Okay, then 2. 2 minus 1 is 1. 3 to the power of 1 is 3. 3 to the power of 3 minus 1 is 3 squared, which is 9, and so on. So it's going to be that same pattern. So we could find a to the 15th and do 15 minus 1 is 14. 3 to the power of 14. Obviously going to be a very big number, but we can keep that same pattern going out. So arithmetic and geometric, we graph these. We can graph them just like functions based on our tables. Our n is our input, our a is our output. We need to know the number of the term in order to calculate the value. And so that's what we'll have. So we'll look at these practice set problems as a class. And then we're looking at lesson 62, graphing solutions to inequalities on a number line. So again, we may have numbers that we're looking at inequalities. We've worked with isolating unknowns when we have an equal sign. It's going to be a very similar process when we have inequalities. So if I have, let's just say, let's just say this. Okay, well, I would combine like terms. It would be 5x plus 2x is 7x. Okay, I want to get x by itself, so I divide, since I'm multiplying both sides by 7. So x would be less than 7. Okay, so I can put any value in less than 7. I could put in 6. I could put in 5, 4, 3, 2, 1, 0, -1, -10, -100, any value less than 7. So this one, we're not solving for just one value, what x equals. We're solving for a range of values. X is less than 7. Or if we had x is less than or equal to, we'd say x is less than or equal to 7. And just in this example, whatever it is. Or it can be between values, okay? Any number between -3 and +5. Or whatever it is. But it's the same process. We still think inverse operations, just like if it was an equal sign. We still do the same thing here. If we're adding, I need to subtract. If we're subtracting, I add. If I multiply, I divide. If I divide, I need to multiply. If I'm squaring something, I need to take the square root. So we still think inverse operations. The one, we'll see if it talks about, but the one thing we may run into if I have, let's say we have, like, well, -x is less than -1. Normally, we would just change the sign. If it was an equal sign, we'd say, well, then x equals 1. If -x equals -1, then x equals +1. In this, since we have an inequality, if I can change the sign, okay, by multiplying by -1, essentially, that becomes positive. -1 times -1 becomes +1. But in this example, okay, I need to, oops, sorry, I meant to flip it. I need to flip that sign. So x is greater than 1. If -x is less than -1, and I'll show you what I mean. So let's put in, let's say x, let's try -3. Well, sorry, let's do +3. So negative of 3, -3 is less than -1. Okay, that is true. But if I change the sign, I have to flip this because, look, put in that same value, x is 3. Well, if I had not flipped the sign, it would be 3 is less than 1, which obviously is not true. 3 is greater than 1. So equal sign, if we flip an equal sign, it's still an equal sign. So that doesn't really matter. But when it's an inequality, if we have to change the sign of one of our signs, we need to flip that inequality. So obviously -3 would be less than -1, but then, okay, the opposite of that, we flip the sign. 3 is greater than +1. So that's why we have to do that. So there may be one extra step that we have to have when we're looking at these. And if we graph them on a number line, if it's greater than or less than and equal to, we have that line underneath, then we're going to use a shaded circle because it includes that. If it's just greater than or less than, we're going to use open circles, because if we say, well, x is greater than 7, in the example I drew up just a second ago, well, x is greater than 7. Well, 7 is not greater than 7. 7 is equal to 7, so we would do an open circle above 7, and then everything to the right. 8 is greater than 7, 9, 10, 11, 12. Okay, so we can use that. Okay, let's look at this one. 3x plus 1 is less than or equal to 7. 3x plus 1 is it greater than? It's less than or equal to 7. Okay, so again, let's not pay attention to this right now. Let's just isolate the variable. We want to get x by itself. We've done this in the past. So I have plus 1, so I do minus 1. 1 minus 1 is just 0. I have 3x. 7 minus 1 is 6. And I divide both sides. Since I'm multiplying, I divide. So then I have x is less than or equal to 2. So on my number line, okay, it's less than or equal to 2. So I know my dot goes above 2. Okay, it's less than or equal to. So 2, if I put in 2 for x, it would be true. So I use my shaded or my solid circle. And that's less than or equal to 2. So every value to the left. 0, hold on. 0 is less than or equal to 2. That's true. -1 is less than or equal to 2. -3 is less than or equal to 2. So every value to the left of that, including 2, would make this range a true statement. When they're in the range. Let's look at this. Vincent goes to the store with $20 to buy a notebook. Okay, for $4, he notices that packages of notebook paper are on sale for $2. Write and solve an inequality. Show the number of packages of notebook paper he can buy if he also buys the notebook, ignoring sales tax. So again, he has $20. He wants to keep it right at $20 or under. He can't go over that because he doesn't have enough money. So P will represent paper. The $4, he's buying that notebook no matter what. So it's 2 times however much packages of paper he can buy, plus the $4 he's spending on the notebook, has to be less than or equal to 20. Okay, so we minus 4 from both sides and then divide by 2. So we get 16 divided by 2. Packages of paper is less than or equal to 8. So he can buy 8, he can buy 7, 6, 5, 4, 3, 2, 1. Okay, we could draw it on a number line representing this. We know since the real world example, they probably won't be happy if we rip open and take a third of a package or a fourth of a package or 0.1 of a package. They're probably going to sell it to us in whole increments so we can buy 8. Okay, and then the line not connecting because 8, and then we can go to 7, 6, 5, 4, 3, 2, 1, or we could buy 0 of them if we want and still be under $20. Okay, so for this real world example, since we have to buy in whole numbers, we want to make sure we indicate that on our number line. All right, practice set we'll go over together and treat it just like an equal sign and isolate your variable, just like we've been doing plenty of in the past, and then graph it. The thing is we're looking for a range of numbers, not just one value. If it's a range of numbers, there may be infinite numbers that satisfy it depending on what we're looking at. That's all we have for today. Next time we'll be looking at lesson 63. Thank you guys. We'll see you here soon.